Alright, this is our first video about equilibrium. Let me pull up my visualizer. I don't want you over there. I don't want you over there. Okay. Alright, so the PowerPoint, I didn't want to have a ton of PowerPoints linked in the module because it just gets really, really long. So I kind of have them together. So this one's called Equilibrium Part 1. It's actually Part 1 and 2. We're going to start with slide 2 of Equilibrium Part 1, and for this video we're just going to do the first 2 bullet points to keep it kind of short. So we're going to define what equilibrium is, and then we're going to learn how to write equilibrium constant expressions. These are extremely important, but easy, not hard, just easy. All right. Almost all processes are in a state of what we call dynamic equilibrium. Dynamic means it's always changing. Equilibrium means it's reached some kind of overall stasis. So, equilibrium is defined as equilibrium doesn't mean nothing changes. When you zoom in, reactants are always converting back and forth into products and then back to reactants. So most processes are not one direction only. You can come up with some exceptions, but generally, and certainly in what we call solution chemistry, which is what we focus on a lot this semester, these are always interconverting. Equilibrium means, in our class, equilibrium is when the ratio of product to reactant stops changing or stays constant. That's just what stays constant means, is that it stops changing. So the ratio doesn't change. But if you zoom in, the molecules, the particles are constantly flip-flopping or switching. I couldn't decide which word I wanted to say. Both of those, flipping and flip-flopping and switching back and forth. But overall, the ratio doesn't change. So let's say at equilibrium, you have 5 product molecules and you have 2 reactant molecules. Let's say that is K, we'll say EQ for equilibrium, and the capital letter K just means constant. We don't use the letter C for constant because it's taken. It's the speed of light, it's specific heat capacity. So a lot of times in science classes, and especially in chemistry, the letter K, capital or lowercase, means constant. Fun fact. Okay, so this means that equilibrium, you have 5 of these and 2 of these, but that doesn't mean they're not constantly converting back and forth. As long as this overall ratio, 5/2, is the same, they can flip across that reaction barrier. Okay. Equilibrium does not mean you have the same number of products and reactants. That's really important. Equilibrium does not mean that products equal reactant. All right, that would actually be an equilibrium constant of 1. So here's an equilibrium constant, product over reactant. This we can call an equilibrium constant. It'll be a number if we specify a reaction and a temperature. We can look up a number for that, this equilibrium constant. It doesn't change unless you change the temperature. It doesn't change. It doesn't change. That's why we call it a constant. This is the let's say just generally amount of product. And this is just generally amount of reactant. Now technically we're either only using molarity of these components or partial pressure if we're in a gas phase. We could use molarity for a gas reaction, but those are our only two options I'll talk about in a minute. Okay, this relationship right here is very important because it tells us if a reaction is product favored, meaning, oh, it's going to go. It is going to form, you're going to disassemble those reactant particles, molecules, compounds, and you're going to reassemble to form product. That's happening when we say it's product favored at that temperature. It means you have more product than reactant. So product favored just means there's more reactant, capital R, than product, capital P, at equilibrium. Okay, so if we use this, oh, this is it right here. This is the secret of the next like 4 chapters. This relationship is very important. It's very simple, but you can use it to solve a lot of problems. Okay, so that means the number on top is bigger than the number on the bottom. So we can actually look at the value of the equilibrium constant. We can look it up. We can look at that number and we can say, oh yeah, that's product favored. Or no, that's not going. That's going to stay over on the reactant side. So if K, the equilibrium constant, is greater than 1, we call it product favored because you have more product than reactant. If this ratio is greater than 1, that's what that means. We also have reactions that are unfavorable. They take a lot of energy to go from one end to the other. So again, I'm going to rewrite this relationship of the equilibrium constant as a ratio. Product is on top, reactants are on the bottom. If this is a small number, if it's less than 1, that means the denominator, there's just math, the denominator is larger than the numerator. So that means you have more reactant, capital R, than product, capital P, at equilibrium. Okay, and that just means it takes a lot of energy to get over that, get over to that other side. To form product, it takes a lot of energy to break those bonds in the reactants. That's what that means. Product favored doesn't mean it doesn't take a lot of energy in those bonds. It just means that your products are going to be lower in energy, basically, than your reactants. Okay, so that's a very simple introduction to product favored and reactant favored. So really quick, we're going to summarize with, let's say we have a K value for some reaction and it equals 4 times 10 to the 32nd. Is that going to be product favored or reactant favored? Think about it for a sec. What if we have another example? What if we have 2.5 times 10 to the negative 6? And equilibrium constants are unitless. Which one of these is product favored and which one is reactant favored? Well, again, we're just using this relationship. If it's less than 1, like this one right here, this is reactant, capital R, reactant favored. Means you're going to have a ton of reactant and very little product at equilibrium. This is a huge number. Greater than 1, for sure. A 4 with 32 zeros after it. Yeah, put that in my bank account. Goodbye, student loans. You know what I'm talking about. All right, capital P for, not pressure, I almost said pressure. Product favored. This is what happens when I'm left to my own devices. Okay, so that is just a really general introduction, definition of equilibrium. I did put a YouTube video on here. I'm not gonna show it for you, but this is what it is. It's a 4-minute video. I really encourage you to pause the video now, navigate over to that YouTube. It's a very clear, it has wonderful animations. So pop on over to that one. Okay, and then when you come back, we're going to do equilibrium constant expression. So pause the video, go watch that YouTube, learn a lot, and I'll see you in 4 minutes and 18 seconds. Oh, you're back. Okay. Equilibrium constant expressions. So we talked about the equilibrium constant as a number. KEQ is a number. You look it up. It's based on the reaction. RXN is my shorthand for reaction. It's based on the reaction, and it's also based on the temperature. Temperature is a measure of heat, which is thermal energy. So if we're changing the relative amount of energy in the system, we're changing the ratios based on the energies of the bonds. Okay, so it is a number, but we also relate it to what we call an expression. You could think of it also as an equation if the word expression is throwing you off. These rules are crucial. Again, this is very simple, but it is a set of rules. You're definitely going to use this in probably a third of your next couple of exams. So this is a very simple set of rules. Okay, so we already know products over reactants. So these are rules for writing the expression or the equation side. So that's a number you look up in a table, or you could solve for it. And then we would set that value equal to an equation or an expression. So the rules for setting up the expression are: number one, products go over reactants. Okay, we talked about that a little bit. I think we're okay with that one. Two is that we don't include pure solids or pure liquids. Nothing that has that S phase after it, or the L, pure liquid, after it. If it has AQ, or if it has G for gas, we include it in the expression. But if it has S, meaning solid phase, or L, meaning liquid phase, we don't. We replace that with a 1. It's not a 0, right? If your only reactant is a solid, your equilibrium concentrate or equilibrium constant expression is not 0, it's 1. Or actually it'd be whatever over 1 if your reactant is just a solid. I'll show you what I mean in a sec. Okay, and the third rule is that the exponents in this equation, this expression, the exponents are equal to the stoichiometric coefficients. Backing up a little bit, the reason that we don't have pure solid or pure liquid in the constant expression is because the concentration or the pressure of these never changes. Well, we don't really measure pressure for solids and liquids, so that's a moot point, but the concentration of a pure solid or a pure liquid never changes, so that's why we don't include it. It's 1. It's a constant. We just put 1. Okay. So this is going to look really weird. I'm going to do a generic example, and then we'll do some real examples. Okay, I'm not sure if this pen is quite thick enough. These do have to be reversible. We are talking about equilibrium, which means this is why we have our double-headed arrow, or our two half-headed arrows going in reverse directions. This has to be reversible, or it can't be at equilibrium, right? The whole point of dynamic, constantly moving equilibrium is these are interconverting. The overall ratio isn't changing. Okay, so if I set up my equilibrium constant expression, I'm actually going to have two versions. I'm going to have one called Kp and one called Kc. Kp is using the partial pressures. And Kc, C is for concentration, so this is using molarity. It's set up exactly the same way. All right, so let's go back to our rules. Products are going to be on the top. Reactants are going to be on the bottom. These aren't designated solids or liquids, so I can assume they're all in the expression. It's just a generic example. And then my exponents are the coefficients. So these coefficients become exponents. So I'm going to use it, do pressure. So K in terms of pressure is going to be the partial pressure of this product, C, to the little c power times, these are multiplied together, the partial pressure of the other product raised to that exponent, products on the top, reactants on the bottom, and they are multiplied. This has to do with collision theory and how many can bump into each other. The pressure of a reactant A to the little a power times, very important, this is times and not added, the partial pressure of B to the little b power. So, very important to note, that's where those come from. The coefficient is the exponent, and this is multiplied, not added. Again, it has to do with collision theory, so how many different ways the molecules can orient themselves and crash into each other to cause a reaction. Now let's rewrite it in terms of concentration. In this case, we're just going to use brackets. So instead of a P for the pressure for gas C, I'm going to use the brackets. This means molarity. Excuse me. I still have the exponent, that is the coefficient. It's going to be kind of hard to see. I still have products on the top and reactants on the bottom. All right, let me see. Can I zoom out? That's the most I can zoom out. All right, so going back, that's my reaction. There's in terms of pressure, right? If I use the partial pressure, that is a capital P, and then the subscript is that gas, whether it's an atom or we could have a molecule like carbon dioxide. The subscript is just the identity of that gas, and the capital P is the partial pressure, excuse me. So that's the only difference. It's still products of reactants, no solids, no liquids. It's still the coefficient becomes an exponent. It's just, are we talking about pressure or are we talking about concentration? Okay, so it's just a set of rules that you apply. So let's do these two examples and then we'll wrap it up for our next video. Okay, and again, multiplied. These are multiplied together. Very important. All right, so let's do KP. I didn't specify in the problem, but I'm going to now for the first example. So we've got, let me write it down here, 3O2 dioxygen gas goes to 2O3. This is ozone. So this is a reaction we see in different layers of the atmosphere, you know, on the surface of the sun. No. Okay, so products over reactants. So this is my product because it's on the right side of the arrow. And P means I'm going to write the partial pressure as the term. I only have one. I only have one, so that means I'm only going to have one term in the numerator. I only have one reactant. So I'm only going to have one term in the denominator. That's it. That's it. Now, I could look this up. If I was given a temperature, I could look it up in a table, right? 25 degrees, what is this value? I'd look it up in a table. And maybe I'm given one of these values and then I can solve for that one, just to give you a glimpse of where we're going. Okay, and our last example for this video, hang on there if your brain's about to explode. Now this one, I'm gonna do KC in terms of concentration, even though I didn't specify in this problem. These are gonna be multiple choice on your exam because the formatting is really a bear and I would not expect you to do that on your test. That'd be pretty stressful. All right. Products over reactants. Oh, but I have a little bit of a twist because solids and liquids are one. So this is my silicon dioxide solid, SiO2. This is sand, or if you heat it up, it's glass. Times, so that's a 1 because it's a pure solid. And then this is my concentration, so I use those brackets. This is water. Even though it says gas phase, we can still get a concentration of a gas, right? You could use PIV-NERT, PV equals nRT. If you solve for N over V, using the ideal gas law, that is concentration in terms of molarity. Okay, I'm forgetting something. What am I missing? You know, it's really helpful if I just write this. I'm just going to rewrite this. Even though you have it on the slide, you don't have to, but I like to have all of the things together on one so you don't have to flip back and forth. So if you feel like you're, that's a gas. If you feel like you're missing something, there's a second screen tab at the top of your Panopto, so you might do that. Okay, there we go. Now I can see what I'm working with. No solid, no liquid, so both of these terms are going to go. It doesn't matter which order you put them in because they're all multiplied together. That's an understood coefficient and exponent of 1 times, this is going to be concentration, and I do need my exponent of 2 because that is my stoichiometric coefficient. It is very important that I multiply, and because I'm multiplying, it doesn't matter, actually if I was adding it wouldn't matter either, but it doesn't matter what order I do this, right? 1 times this term is the same as that term times 1, right? This times this is the same as O2 squared times this silane, the silicon compound. No matter which order, it's the same value. Okay, very important, very, very important that you practice setting up these equilibrium constant expressions. It's simple, so the more you practice, the faster you'll get. All right.